Hey everybody, welcome back. Make sure I'm sharing the whole screen here. 12.4, the final thing we're looking at is finding the planes that are generated in this. We had the tangent, normal, and binormal vectors. This is called the Frenet frame. And we used to have IJK. Now we're going to work with T, N, and B. The TB plane, which is right here, is called the rectifying plane. The TN plane, which is down below, is called the oscillating plane. And the NB plane is called the normal plane. A picture of it, I'll bring it up from the book real quick. Take a look at it. They show those right there. Did I say oscillating? It's osculating. My bad. Terrible names, right? Rectifying and osculating and normal, lame. But more along the lines, this is what I wanted you to look at right here. So that section right there, we're gonna look at that. We've got at any given point our tangent vector, our normal vector, and then our binormal. The tangent and normal vector, that's the tangent normal plane right there. And you can see we have three orthogonal vectors. As we move along the curve, these planes change. Okay, so keep that in mind. Let's go back to just looking at an example. So the osculating plane, my bad. We're going to find planes at t equals 0 for the function r of t equals e to the t cosine t, and e to the t sine t. We can see that r of 0 is 1, 1, 0. That's good. And using finding t our regular way, r prime over r magnitude of r prime and t prime over the magnitude of t prime, it can be shown that t and n are these formulas equations right here. If you don't believe me, you can go through and do the work. I omitted it to save time. It's just derivative work. It's a pain in the ass. Maybe we can do that in class as example 2. So if I evaluate t and n at 0, I get t0 is 1 over root 3 for all three components. And n0 is 0, negative 1 over root 2, and 1 over root 2. If we do the cross product, we get b of 0 is 2 over root 6, negative 1 over root 6, and 1 over root 6. Again, you can do those calculations and check. I wanted to go over the planes. So let's take a look at the planes. If we look at the TB plane where n is normal, we had R0. R at 0 was 1, 1, 0. Remember, this is a position vector, so it's pointing to the point. That is a point in our plane. So we will use that along with the normal vector to do n dotted with PP naught equals 0. So the normal vector for the TB plane is the n is negative 1 over root 2 and 1 over root 2. We multiply it every single plane has x minus 1, y minus 1, and z, because all three planes share this coordinate. You go through and you work it through, you multiply, do the dot product out. You get to this, and I could have done it up here in later steps, later planes I will. We don't need to use the square root of 2. Notice if I multiply both sides by the square root of 2, on the left side, it just magically cancels out with each of these on the inside when we distribute. And on the right side, 0 times root 2 is just 0. Don't deal with the roots if we have to. We want nice simple coefficients. I've got 1 right here. This is 1. This is minus y, and this is plus z. So 1 minus y plus z equals 0. Or if you want to write it with the constant last, we can do such. That works too. For the TN plane, B is the normal vector for that plane. We're going to use the same point. The B vector was 2 over root 6, negative 1 over root 6, and 1 over root 6. So we do this here. The dot product is that. I don't like that root 6 in the denominator. I'm going to multiply both sides by the root 6. Just like we did up here, it clears it out. I'm left with 2 times x minus 1 minus the quantity y minus 1 and then minus z. And when we distribute and gather like terms, we have 2x minus y minus z minus 1 equals 0. And finally, for the NB plane, T is the normal vector. That was the one with all the root 3's in it. And I'm writing it like this because I can. You can factor out the 1/3 and use 1, 1, 1, which makes this a little bit easier. This dotted with this is just these things added together. X minus 1 plus y minus 1 plus z. The 1 over root 3 is on the outside still. I didn't get rid of it. It's still here. But I can, again, multiply by root 3 on both sides, and it just cancels right out. We do root 3 over here. That's still 0. So I have x minus 1 plus y minus 1 plus z. We get x plus y plus z minus 2 equals 0. That's it for 12.4. This is a doozy. We're going to spend 2 days on it in class. It's a lot of algebra. I know. I'm sorry. It can't be avoided. I think partial derivatives are easier when we get there. You'll like chapter 13 more, but we need some of this stuff. Peace.